I'm gonna start now. So, hello everyone. My name is Kasper Piskorski. I'm an R&D engineer at Grakn AI. So what we do at Grakn is we try to enable databases with AI technologies. So the startup has been founded in Cambridge 3 years ago, and we are still running and going strong. And today I'm gonna talk to you about merging the relational, the graph, and the semantic. So I'm gonna talk about actually why to do that, why even be bothered. I'm gonna talk about the use cases for that, the application, and I'm gonna go through the particular, basically how we did that in the end, and what it allowed us to achieve. So there were many sources of inspirations to do that. So basically the why part was established on grounds of both development work as well as exposure to specific technologies and reading materials. So the first impulse or inspiration was the semantic search. So some of us used to work in a startup that used to build semantic search engines. So semantic search is this peculiar type of search that actually gives you fewer results rather than more. So the whole idea is to provide the user with more specific and more tailored answers to his questions. And so how it is done is actually by exploiting the meaning of data and exploiting the relationships that exist between the data in question. So what that requires is actually something called explicit semantics, which gives the context for our data so that we can understand it better. And so that was the first inspiration. The second one was basically the discovery of expert systems. So expert systems were these devices that tried to mimic the way human decision making is actually working. So they were really popular in the 80s, and they didn't really live up to the expectation of providing a system that would allow answering questions at an expert level. So what's characteristic about them is that they contain two components. The first being a knowledge base, which contained all the facts that we know about our domain of interest, and the knowledge base was accompanied with a reasoning engine, which sole task was to take your facts and combine it with rules, which were simple statements in the form of when something is true, then something else is true as well. So the way they worked is they took a domain expert and made him come up with the rules which captured the patterns specific to a given domain. So having the rules defined, having the facts, we could basically provide the query answering mechanisms as well as providing recommendations or just in general facilitating this decision making. The third inspiration was the general AI applications and the realization that very often they have to deal with either complex domains or data that goes beyond the structure of simple linear data. So in order to achieve intelligent management of data and processing, we need to be a bit more clever in the way we handle our information. So we have three systems here, and they look somewhat disjoint. However, they share one particular common denominator. So the denominator is something that's called cognitive systems. And the idea behind them was to emulate the way human cognition works. So at the heart of such systems, we have the equivalent of a human brain. So we have the knowledge representation component, which provides a specification of how do we want to model our data. It contains the storage component, which stores the information, and it's equipped with an inference engine, which basically allows us to deduct, reason, solve problems, and so on. So we as humans actually record all kinds of information passively by reading the information coming from our senses. We also do it actively when we pursue specific information we are interested in. So in cognitive systems, the component that's responsible for that is the knowledge acquisition component. So what's the role of it is to provide a way of retrieving information and transforming it in a way that our brain or our knowledge base will actually understand. So that's the knowledge acquisition. As we all know, as humans, we are capable of learning. So in cognitive system world, that corresponds to the machine learning component, which basically allows us to find patterns, identify patterns, learn on previous experiences to allow us to do judgment and evaluation. The final component is the natural language processing component, which is responsible for the communication part. And the carrier of information here is our natural language. So this is the common denominator of all the systems I actually mentioned a while ago. And because there is a common denominator, there's also a list of problems that are shared among such systems. So there are three main problems that if we want to build systems that can mimic in some way the way human cognition works, is we need to address those three problems. So the first problem is the problem of structure. So in order to intelligently process our data, we need to give it some specific structure that would allow us to retrieve meaning out of the data we have. So that's the first problem. The second problem is the problem of complexity. So the model our data follows, the model we want to model our data in, needs to be expressive enough to accommodate things we want to actually talk about. So our model basically needs to be able to describe the domain of interest to the extent we want it to. And the last problem is the problem of scalability. So once the system is built, we might want, or probably will, want to extend it to cater for increased data loads and workloads. And for that, we need the ability to scale. So I'm going to focus on the two first problems and leave the scalability at the end. So if you look at the problem of data structure, so what does it actually mean, or what are we lacking, or what are we missing if we work with unstructured or loosely structured data? So the first immediate problem is the problem of integrity. Because the structure is very weak, we are lacking any kind of we have little control of whether our data is valid and whether it's consistent. So that leaves us in a difficult position because we cannot put any guarantees on the consistency and validity of our data. So the second difficulty that comes with unstructured or loosely structured data is when we consider its accessibility and retrieval. So if we are dealing with simple structures, again, having meaningful query answering mechanism is hard, and it's harder to do it efficiently. The third point is maintenance. which is connected also to the first problem. So because we have little control over the data, it's hard to maintain it, it's hard to make changes to it, and it's hard to propagate them. Finally, starting with little structures, okay. However, by doing that, we are only pushing the responsibility of defining the structure later. Because I don't think we can afford having unmaintainable applications which are error prone. And that's basically just deferring in time the need for structure, which means extra logic at the up level. So that's the problem of structure. So what comes with complexity? So if we have complex data, what happens? Complex data is harder to model. So current models are typically tailored for binary relationships, which means they have difficulties with capturing complex domains and complex relationships between data. So what else is complex about complex data? Complex data is complex to query. So current languages only allow you to store to actually query the data that's only explicitly available. They are also very, well, reasonably low level, which means that queries that are conceptually simple are quite verbose. The third point, or the third thing that comes with data complexity is the analytics being expensive, which means complex data makes reuse of distributive arguments harder in general. So to sum up, what we think about complex data is that we require some kind of abstraction, which is accompanied by a matching structure at the database level in order to provide the user with a mechanism to query your data. So we have those problems, and we know that typically storage and data representation means a database in computer systems. So we can translate those requirements, we can translate those problems into requirements that we put on our backend. So if we know the structure is problematic, then we know that we need some kind of explicit and high-level schema at the database level. So this is in order to guarantee some kind of consistency of our data. So if we talk about complexity in database world, it means our data model, or the data model that our database follows, needs to be expressive enough to capture the kind of things we want to talk about, to model, and it needs to capture the complexity of the domain. So last point is the problem of scalability, which for a database means it requires scalable architecture, and it also puts some kind of bounds on the expressivity, because having models actually too expressive means more complex processing and basically making efficient algorithms hard as well. So these were our requirements for the backends. So because we don't want to reinvent the wheel, we first look at what's out there already. So if we look at those three problems, then there are basically three possible perspectives of approaching them and giving the guarantees of consistency, flexibility, and expressivity. So I'm sure everyone knows the relational approach, which is the most mature one, which is basically relies on modeling your domains by means of relations or tables, which are sets of tuples. So this works very well for record-based data, so like financials, commercial data, administrative data, and the idea is that when you define your relations, you are effectively fixing the schema of your application. So the plus side of that is that consistency is maintained by a consistency checking mechanism, but the minus is that we lose flexibility. So basically any changes to our model are hard or even impossible. That in practice means that we need to know how do we want to model our domain before we start working with our application. So there's a flavor of SQL, which is the new SQL, which basically allows you to scale the relational model implementations, and which offers horizontal scaling as well. So basically, by starting with a scalable architecture, we can achieve scalability. However, we are still lacking explicitity. So the opposite approach is the noSQL approach, where we start with no schema or very loose schema, but that allows us to have scalable systems by design in most cases. So that's great if we want to prototype things, if we want to change our models, redefine our concept and so on. However, when we hit production and serious applications, we again have the problem of having to define and put constraints on how our data is structured. So the last approach is the semantic web approach, which is not really tied to any specific database. This is basically a collection of technologies that originally were aimed to annotate the web and make querying it and make information exchange and retrieval manageable. So semantic web offers different data models. So some of you might be familiar with the with OWL, with the web ontology language, which comes in 3 flavors, each offering different constructs to build your schemas in. So we have also the data format, the RDF data format, and then we have all the accompanying technologies. So the problem with this approach is that there is no one single solution that gives you end-to-end, that basically gives, there's no an end-to-end solution offered by any particular technology. What you have to do is to gather all the scattered bits and combine them yourself, which is not always actually trivial. So these are the approaches, and now let's put some faces to it. So I'm sure you know the Oracle SQL implementations. So we have Microsoft SQL Server. On the relational side, we have SAP, we have PostgreSQL. In the new SQL world, we have CockroachDB. So if you want to start with flexibility, we have MongoDB, which is a document store. We have property graph provided by Neo4j. We have multimodal databases like ONDB, and well, last but not least, we have efficient key value stores like Cassandra. So in semantic web, I already mentioned OWL, which is the web ontology language. We have the Sparkle query language, which is the language for RDF, and we also have specific backends which come in the form of triple stores. So I think this is Allegro graph here. So we also have other ones like Virtuoso, and they come in different flavors. So it could be graph, could be key value store, could be even relational. So that's what's out there, and what we actually wanted is to be somewhere in the middle or relatively close to it. So, which you can see cannot be really achieved with anything that was out there, or not easily. So what we did instead, we built Grakn. So what is actually Grakn? So Grakn is a database, and in fact it's an open source database we've got available on GitHub. It comes in a flavor of knowledge graph, which is just a knowledge base expressed in terms of a graph. So it rests on a high level flexible data model, which I'm going to explain in a moment. And we equipped it with our own query language, which is high level enough that you don't have to be worried about particular representation of your data at the very low level. So what we achieved by doing that, and I'm going to explain the details in a moment, is we have the logical integrity like SQL. We can represent complex relationships, and we can scale horizontally like noSQL databases. So now let's look in detail on how do we actually do that. So how do we solve the three problems that I mentioned at the beginning? So how do we handle consistency? We handle consistency by first defining a high-level data model. We refer to it as the meta schema. So now when we are creating applications, for each applications we create an application-specific schema which needs to follow our meta schema and needs to be conformant with it. So the way we actually check for consistency in this case is done on commit time. So once you actually define your schema and you want to persist it to the database, and you actually write commit, we will check whether the provided schema is consistent with the meta schema. So that's how you define application-specific schema. Now what about the data? It actually follows the same pattern. So at the moment you commit a transaction, so when you're actually adding data to your database, when you're persisting it, we do a check for conformance of provided data with respect to the schema you define. So that means both consistency as well as validity. So that's the top-level view of the mechanism of consistency checking at commit time. So now let's look how the model actually looks like. So our meta schema, so the schema of all schemas, is a collection of top-level concepts from which you derive all your application-specific types. So we differentiate three different types, being attributes, relationships, and entities. And all application-specific types need to be derived from these ones. So apart from having the top-level concepts, we also define the primitive relationships between them. And so for example, so we allow entities to have attributes, we allow relationships to have attributes, and we define relationships by specifying the roles that can be played in relationships. So role is a way of quantifying the nature of participation of role players in a relationship. So for people familiar with the entity relationship model, that should look already familiar. So that's how the top-level schema looks like. How do we define a schema for now? So the process of defining a schema can be seen as subclassing the meta schema. So here in the example, we have the relationship of employment. So we say that in this relation we have two roles, which is the role of an employer and an employee. And we specifically constrain this relationship and say that only people can be employees and only companies can be employers. So that's an example of a schema definition. And now we can look at an example at the data level. So we defined our employment relationship, and now we want to say that there's a specific person as well as a specific company that actually are embarked on a employment relationship. So as you can see, the process of defining, well, of creating data is the process of instantiation of your schema elements. This also shows you nicely that if you look at the data alone, it has little meaning without looking at the specific context, which is the schema. So that's how our model looks like. That's how you define things. So that's how we solve the consistency problem, or that's our solution to the consistency problem. Now let's talk about explicitity. So I'm sure all of you know how a regular graph looks like. So we have a collection of vertices, we have edges, and the important point is that a single edge joins only two vertices. So we can extend that to be able to express more complex relationships by turning it into a hypergraph. So what is actually hypergraph? Hypergraph is a graph with hyperedges. And what's a hyperedge? So hyperedge is a generalization of an edge to cater for the case of general number of things it is connected to. So in this case, we have two hyperedges, which are marked with the circle, and they enclose 4 vertices in this case, and 3 vertices in this case. So okay, yeah, we have a hypergraph, which is a structure known in mathematics. But what does it actually mean, we have a hypergraph? So we can then express hyper-relationships. So we can, if we want to say there's 4 people that each know each other and are friends of each other. So let's say we have Alice, Bob, Charlie, and Dave. Then friendship looks like that in our world. We can simply enclose all the vertices that take part in this relationship with a hyperedge. Similar for employment. So if Dave works for a specific company on a specific contract, this is our employment hyper-relationship. So, having defined that, we can start talking about the interesting things, which is the query language, and how do you actually access those well, conceptual figures in practice. So we came up with a language that we call Grakn, which is a declarative language, which we wanted from the beginning to be human readable, and which serves both as the domain, as the data definition, as well as data manipulation language. So all this is actually how the grammar of, well, that's like an excerpt from the grammar of the language. So don't worry about the details, but the key point is that we define different types of queries that fall either into the data definition or data manipulation category. So data definition, it means how we refine our schema. So we have defined and undefined keywords for that. And for data manipulation, we have match and get queries in order to fetch and retrieve data. We have insert and delete for insertion and deletion respectively. And we have some extra analytics queries that allow to do computation and aggregation queries. So that's the top level view. So how do we actually define things? And how do we actually add data to the database using the language? So here we have a simple schema, just to make things more interesting. This time we have 3 rows. So we have an extra row, which is the employment contract. So we say that our relationship of employment relates the roles of employee, employer, and employee contract. We say that only people can be employees. We say that companies can be employers, and we say that contract well, contracts can, in general, play the role of an employment contract. So it doesn't have to be employment contract, we can also have other contracts as well. So you can see there's this mechanism of subclassing the meta schema each time over here where you see the sub keyword. So a person is a subclass of an entity, company is a subclass of entity as well as contract is, and employment is a subclass of relationship. So what we also allow is to characterize our types with specific attributes. So both people and companies have names, people have social security number, contract has a starting date and a specific salary. So attributes are also subclass for the meta attribute, where we also specify the specific data type we are interested in. So that's an example of a simple schema. Now let's add some data. So if you remember, adding data corresponds to the process of instantiation of schema elements. So we have a particular employment relationship between a person called John and a company called Oculus, which the employment involves a specific contract, which is characterized by the attributes of a specific start date, a specific salary, and people familiar with Prolog should find the definition of relationship familiar somewhat. So we just say that the variable mapping, all the concepts that map to the variables, we assign them a specific roles in a relationship of type employment. So because we already have the subclassing mechanism, we also added support for type hierarchies. So which reminds us the object-oriented paradigm and how things are structured. So we can, for example, say that startup is a specific case of a company. So startup specialized company, and customer a specialized person. So in that way, the properties of parents are inherited. So we don't have to define them again. So in this case, because people play the role of employee and companies play the role of employer, we know that both startup and customer can play their respective roles as well. So that's type hierarchies. So now the actual reasoning part. So what we allow to the user to model is the capture of dynamic patterns that actually show up in the database. So this is the same idea as the one employed in expert systems. So basically we have we define patterns or rules in a form of when something is true, then something else needs to be true. So in that way, in this example, we can say that if two specific schedules overlap, then we want to add the next relationship between the concept that actually correspond to the schedules. So that's an example of how it's done in practice. So so the language is equipped in a full reasoning component, which allows you to write rules, to chain them, and again, for people familiar with Prolog, I'll just say that we use resolution to actually resolve queries that involve reasoning or patterns that are not defined explicitly. So another way of looking at it is by defining relationships that are virtual. So we don't have to specify all the knowledge explicitly. We don't have to persist it. We can just say that there are certain patterns that are in our database, or we expect certain patterns in the database that basically yield some implicit information. So the last problem that we address is the problem of scalability. So the way to actually handle that is by design. So basically, so we define all the high-level data structures which are handled by Grakn server. Meanwhile, the actual internal storage is handled by a scalable key value store, which in our case is Cassandra. So there's a mid layer, which is the one that's responsible of switching between the high level and the low level representation of data, and this is accomplished by a specific graph API, which is the Janus graph. So why the particular choice of those two components? So both Cassandra and Janus graph are open source. Both are known for scalability. Both are to some extent tunable. So for example, Cassandra, you can tune consistency to the level you desire, and yeah, basically that's how a single node is defined. So then the idea is, if your workload or data load requires more power, more processing power, you just keep adding extra nodes. So that's the top-level architecture. The second interesting bit is how we handle communications. So the flexibility comes from the fact that the user can use languages that he sees fit. So he can use either the language that's native for him or the language that he prefers to program in. And because the way we handle client-server communications, he can access remote objects and methods as if they were local. So the way to do that is to use gRPC, which is the Google technology for remote procedural calls. So that basically leaves all the communication part and communication details handled by gRPC. The interesting point is that all our queries are executed lazily. What that means is you don't have to fetch all the results of your queries immediately. Basically, the user only gets as many results as he sees fit. And the way to realize that in practice is to use iterators within the context of gRPC. So the basic idea is that we store the state of querying, and we are able to restore this state if user sees it fit. So basically this allows us to speed up some of the querying where extra processing is not necessary. So to sum up, our goal was to be able to build cognitive systems, and to do that we needed to address three problems, being consistency, consistency, flexibility, and expressivity. So we did that by devising a knowledge graph. We equipped the graph with a high-level query language. The query language works on a specific data model, which is a flavor of flexible entity relationship model combined with some hypergraph concepts. We provided automated reasoning to handle the reasoning part, so which is an integral part of the language. And we also provided distributed analytics, which I didn't mention today, but I think it's out of the scope of this talk. So that concludes my talk. Thank you very much. Are there any questions? Or what are the questions? Anyone? Someone? Okay.
What does it actually what does it look like from the user side to actually make a query? If you're designing like a web application or something, what does it look like for me to actually make a query of the database?
What does it look like? So queries are, you can either provide queries as simple strings, or you can use the API to build them with your native language. So the idea was to make it human readable, so there's no ambiguity when specifying queries. Another aim was also to make it less verbose than, for example, complicated SQL queries which involve multiple joins. Anyone else? Okay. I think so. With me here are my friends from the startup. So if anyone has any questions, not necessarily related to this talk, but in general, and dealing with complexity or structure of AI applications, please give them a shout. And otherwise, that's all for me for today, and thank you.